So this picture illustrates a bit more the OFDMA time-frequency multiplexing of several users. Again, the available bandwidth is organized in resource blocks of each 180 kHz, which is 12 subcarriers. So one UE can be assigned either one resource block, an example for this would be UE2, or multiple resource blocks, like UE1 has been assigned 3 resource blocks to transmit on. The subcarrier spacing is 15 kHz, and we can now see that each 1 millisecond these assignments can change. So the time domain in LTE is organized in subframes of each 1 millisecond, and one subframe corresponds to a transmission time interval. So every 1 millisecond we can change the scheduling decision, the base station can change the scheduling decision, and the distribution of the resource blocks among the users can change. Or it can also be maintained for the example of UE2. Now there's also the notion of a slot, which is 0.5 millisecond, corresponding to 7 OFDM symbols. The slot was introduced, for example, because the downlink reference symbols, also called the pilot symbols, are repeated every slot, so that's why it's also useful to have this notion of a slot. But for the resource assignment, again, the transmission time interval of 1 millisecond or subframe is the important part, because this defines the scheduling interval. So note that each UE can transmit with another modulation scheme, so depending on the radio link quality for each UE, either a more robust scheme like QPSK or a more sensitive scheme like 64QAM can be assigned. Now let's have a closer look at the spectrum flexibility in LTE. We have seen that the physical layer supports any bandwidths from 1.4 MHz to 20 MHz in steps of 180 kHz, which is the resource block definition. But we've also seen that the current LTE specifications support a subset of 6 different system bandwidths for FDD and TDD, as they are also shown in the table. So this is these values of 1.4 up to 20 MHz, each corresponding to a certain number of resource blocks. The figure illustrates a bit more that the transmission bandwidth, which is actually then used in the downlink, for example, by the base station, is formed by the assigned bandwidths in terms of active resource blocks. The available channel bandwidth is a bit larger than the actual transmission bandwidth configuration of the cell, to leave some guard on both sides of the spectrum. Also important to note that all UEs must support the maximum bandwidth of 20 MHz, even though there may be smaller cell configurations available, and not all networks may support the 20 MHz depending on the spectrum that the operator has available. This slide shows the LTE frame structure type 1, which is the one for FDD operation, frequency division duplex. We have here the radio frame, which is defined as 10 millisecond, and that is the same definition as in wideband CDMA. One radio frame contains 10 subframes, and one subframe contains 2 slots. Now let's have a closer look to the subframe contents. So a subframe of 1 millisecond is illustrated here in this screenshot of a signal generator from Rohde and Schwarz. And as you can see here, this is a real signal. The x-axis is showing the time domain. So we see here an extract of 1 millisecond or 14 OFDM symbols for the normal configuration. And on the y-axis you have the frequency domain with 50 resource blocks, which is a 10 MHz signal. Now what is the contents of each subframe? In the beginning of each subframe there are certain control channels located, layer 1, 2 downlink control channels. So they, for example, carry information about the scheduling decisions for the different UEs in a cell. So the UE would first read on these downlink control channels in order to get information whether there's resource assignments with user data inside the subframe coming up. So the actual user data allocations are represented in green on this picture, and you can see in this example that actually 2 users would share the available 10 MHz bandwidth, which is really just an example. You can also see at certain allocations downlink reference signals, and you can also see in this special subframe, which is the first one in a radio frame, there's also certain synchronization and broadcast channels. So we have here in the middle in blue the primary synchronization channel, the secondary synchronization channel, and the physical broadcast channel PBCH, which are carrying predefined information important during cell search, which will be explained by Andreas in more detail later.
Christina, one question to the time plane showed by the signal generator. So what does it mean with the hashed area over the entire bandwidth? Can you explain that a little bit more in detail?
Yeah, of course. So the downlink reference signals, which are indicated here by the hashed areas, they are actually not transmitted over the whole bandwidth, over the whole 10 megahertz in this example, but it's just indicated here the symbols which are carrying the downlink reference signals at specific locations inside. So it's specific subcarriers inside the indicated symbols here. So it is just for simplifications that we have hashed here these areas. And accordingly, this picture shows the LTE frame structure type 2 for TDD, time division duplex. The radio frame structure is the same also for TDD, that's 10 millisecond, subdivided into 10 subframes of each 1 millisecond. And we have also the notion of a slot of 0.5 millisecond. But of course, since it's TDD, there's a significant difference here, because in TDD we have uplink and downlink separated in the time domain. So this needs to be somehow reflected in the subframe structure as well. So let's also have a closer look at the contents of a subframe. So the table shows the possible uplink downlink configuration. So we have actually 7 different uplink downlink configurations defined for TDD. And as you can see here, it's indicated for each of the subframes of a radio frame, whether it's carrying a downlink, denoted by a D, an uplink, denoted by a U, or whether it's a special subframe, denoted by an S. And you can also see that there's configurations with a downlink to uplink switch point periodicity of 5 or 10 milliseconds to select from. So let's have a closer look at one example. Let's have a look at the uplink downlink configuration 0. Which is also shown in the screenshot again. So we have represented in the screenshot the 10 subframes, and so the subframe 0 would be a downlink one according to the table. So this is a downlink signal, and the green part is actually showing that there's user data in downlink carried in there. And again, subframe 5 is carrying the downlink data again. Then we have special subframes in subframe 1 and 6. The special subframe is actually carrying a downlink pilot time slot, a DWPTS, an uplink pilot time slot, a UPPTS, and a guard period. Guard period for TDD operation to switch from downlink to uplink. So downlink and uplink pilot time slot are used for regular data transmission as well. But they are just shorter because this special subframe has a specific configuration. Now the gray subframes which are indicated here in the screenshot, they are representing the uplink transmission. They are available for uplink transmission in this specific uplink downlink configuration 0. Also for TDD you have certain layer 1 and 2 downlink control channels defined at the beginning of each subframe, and you have also certain primary, secondary synchronization signals and a physical broadcast channel defined.